So I guess it's time to start. So welcome all of you to the second day of the SAZERAC SIP meeting on models and simulations of high-redshift galaxies. I would like to remind the audience to write your questions in the Slack channel, in the thread next to each speaker. So the first session is called the role of dust, and the first speaker is Madeline Marshall. Can you please share your slides, Madeline?
Yeah, sure. Shall I go?
Yeah.
Okay. Hi everybody. My name's Madeline Marshall. I'm a postdoc here at the NRC Herzberg in Canada. And today I'm going to tell you about a paper that we put on the archive this week using the blue tide simulation to study the sizes of galaxies in the early universe. So if you were to make an observation and discover a high-redshift galaxy, I would argue that one of the most simple things that you could do would be to study what measure its size. And so that's exactly what a lot of observations using deep Hubble fields have done. And so here you can see some observations from Kawamata and Shibuya et al. Showing the radius of the galaxy as a function of its luminosity. And so what all of these observations have found is that, as you would expect, galaxies in the early universe are small as they grow over time. And also there's a positive relationship between size and luminosity. So the brighter galaxies, which are on the left here, are larger. And so this is something that we can also see in models and simulations. So for example, here we have some work that I did a little while back using the Meraxes semi-analytic model. And again, you can see this positive size luminosity relation in the blue here. But to get a really good handle on the sizes of galaxies and see how their properties vary with different wavelengths and dust, for example, one of the best things that you can use is hydrodynamical simulations. And so this has been done in the past, so in particular with the cosmological zoom-in simulations. Ma et al. Studied hundreds of quite faint galaxies at redshift 6 through 10 with very high resolution. And then to look at a much larger sample, it's also been studied using the SIMBA cosmological simulations by Wu et al. 2020, who studied 5,000 galaxies that are much brighter at redshift 6. And so these studies are great and can tell us a lot about what the sizes of galaxies can look like and what simulations expect them to look like under certain models. But these samples are obviously limited to pretty small sample sizes and because of their limited volumes. And so really we'd like a much larger sample of galaxies and particularly a sample of brighter galaxies that we don't see in these smaller simulations. And so that's exactly where blue tides can help. So blue tides is the largest cosmological hydrodynamical simulation to be run. So it has a box with volume almost 600 megaparsecs on the side. So the resolution and particle information is given here if you're interested, but I'll play a video just to zoom in on the simulation to see a couple of galaxies that formed, just so you can get a feel for what the simulation is looking like. Now, because of the extreme volume of blue tides, it's very computationally expensive. And so that means it's only been run down to redshift 7. However, by redshift 7, we have a sample of 100,000 galaxies that we can now study the sizes of and various other properties. So today I'm going to talk about particularly the galaxy sizes at redshift 7, but in the paper we did study redshifts above that as well. So how do we extract the size of a galaxy from this raw distribution from blue tides? So there's a lot that goes into the modeling and I don't really want to go into the details today, but we use software called SynthObs, which was developed by Steve Wilkins and is publicly available on GitHub if you're interested in making mock images of your hydrosims. And so basically we assign an SED or spectral energy distribution to each star particle in a galaxy using the BPASS model. And then we model dust attenuation through a few processes. The most important process that I'll briefly mention is the dust from the ISM or interstellar medium. We use a very simple model here, so a flat slope, a slope of -1, and normalized to match the UV luminosity function at redshift 7. However, so while this is a simple model, this kind of accounts for the fact that the dust properties at high redshift, as I'm sure you're about to find out, are very uncertain. And so I did want to mention, though, that we studied a wide range of different ISM dust models in our work, and we found that none of the results that I'm going to show you today actually change. They're just, they change slightly in number, but qualitatively everything that I show you is holds regardless of that dust model that you choose. But if you're interested in knowing more about that, please read the paper or chat to me about it. So once we have these intrinsic and dust attenuated SEDs for our stars, we can then grid up the galaxy into an image. And so for this, we assume we're looking at the galaxy in the face-on direction. We make 6 by 6 kiloparsec images with 0.1 kiloparsec pixels in very standard breast frame top hat filters ranging from the far UV all the way to the H band. And so one thing to note is that there is no noise in these images, and we're not trying to replicate any telescope observations in any way. We're simply just looking at the wavelengths, gridding up the wavelengths and seeing how size varies with that. And then so once we have all of these images, we then can measure the effective half-light radius. So we use an effective half-light radius, which is a little bit more robust at high redshifts than using the actual half-light radius measured from apertures. But again, I can talk about that later. So this, once we've got this, basically we get a whole host of images, which is probably more useful for you to see. And so here I've got a sample of 6 different galaxies from the blue tide simulation, ranging from our smallest galaxies at 10 to the 8.5 solar masses all the way to some of our biggest galaxies at 10 to the 7.5 solar masses, sorry, 10 to the 10.75. So our left column is stellar mass. So ignoring everything I just said about the spectral energy distributions, just what is the distribution of the stars in that galaxy? The second panel is a young stars, so I believe it's less than 10 million years. What is their intrinsic distribution? And then we look at the SEDs. So here's the intrinsic far UV images. Then we've got dust attenuated far UV, V and H band images, and then finally a color composite of these 3. And so I'm going to refer back to this plot and pop it up again a few times as we go along. But this is just to give you some idea of what kind of things that we're looking at. So to start with, we consider the size-mass relation. So from these stellar mass maps here, so we've got the half mass radius as a function of stellar mass. So blue is all of our blue tides galaxies. The line is the line of best fit, and then the circles are just binned values. And so what we find is that there's an inverse relationship between size and stellar mass. So the most massive galaxies are more compact and dense than lower mass galaxies. And you might not find this completely intuitive, but you can see by looking at these images. So remember, the most massive galaxy is at the top and the least massive galaxy is at the bottom. You can see that these most massive galaxies have very quite compact, smooth distributions. The galaxies are quite settled, whereas these lower mass galaxies really quite have flat stellar distributions and certainly spread out a bit more. And so you can see that the size that you would measure for this object is larger than this one, hence this inverse relationship. So we see an inverse size-mass relation, and we also see this in the size to intrinsic far UV size, intrinsic far UV luminosity. It's a little bit flatter, but generally still kind of the same trends. And so we find that the median galaxy size in the intrinsic far UV is about 0.5 kiloparsec. So what happens though when we include the effects of dust and consider the dust attenuated far UV images? Well, then we get something that looks quite different. So here on the left is the, again, the half-light size as a function of luminosity. And you can see that we've got a positive size luminosity relation with sizes getting larger for brighter galaxies. And so the only thing that's different between these 2 panels is the dust attenuation. And so this implies that the positive far UV size luminosity relation is driven by the effects of dust. And so you can visualize what's going on by looking at these 2 columns on the left. So we've got our intrinsic images, on the left and then the far UV on the right, the dust attenuated. And you can see what's happening is that in the bright regions with lots of young stars, there's more there's more dust. And so that brighter emission is being attenuated and the galaxy profile is getting flattened out. So you're missing that bright emission in the center here and seeing that more extended and therefore measuring larger galaxy sizes. So this is more obvious for these more massive galaxies here. The least massive galaxies don't really show much of a difference. And hence, that's what's causing this positive relation. So more massive galaxies have their, and brighter galaxies have their sizes boosted, and lower mass galaxies do not. And so if we think that this positive size luminosity relation is driven by dust, you might ask, well, how then does the relationship depend on wavelength? So here we have the half light radius as a function of luminosity again. So these are lines of best fit for different filters ranging from the far UV in the purple all the way to the H band in the red. And so the contours show the distribution. So for the purple was the far UV and then the red is the H band. And so what we see is that the slope of the relation actually decreases and then becomes negative as you go from the far UV through to the optical. And so what's happening here is that at redder wavelengths, you have less dust attenuation, and therefore your relation is tending towards that intrinsic relation. Now, at the moment, we're really limited to studying galaxy sizes in the far UV, so in the purple bands here with Hubble. But with the launch of JWST later this year, hopefully we might be able to start to actually measuring in detail the sizes of a lot of these galaxies in much redder wavelengths. And so we might be able to actually start to test this hypothesis of why we see a positive size luminosity relation. So to sum up, if you measure the sizes of galaxies from their mass distribution in the blue tide simulation, we find that massive galaxies are actually smaller than less massive galaxies. If we measure their sizes from their intrinsic far UV luminosity distribution, we find again that luminous galaxies are slightly smaller. However, if we consider their dust attenuated far UV luminosity, we find that luminous galaxies are bigger. And so this implies that the positive size luminosity relation in blue tides is caused by dust attenuation. And so this blue tides prediction will be potentially testable with JWST very soon and will really help us understand what's actually going on at these high redshifts. So today I really spoke about just what's going on at redshift 7 for our galaxies, but in the paper, we also studied redshift evolution and the sizes of quasar host galaxies. So if you're interested in either of those things, please check out the paper or feel free to chat to me on the Slack or by email. Thanks a lot.
Thank you, Madeline. So I don't actually see any questions in Slack right now. There is plenty of time for questions if anybody wants to ask something.
I see Maxime
has his hand up.
Yeah.
Okay, Maxime, can you please go ahead?
Yeah, thanks a lot for the talk. I was just wondering, when I see the size versus mass, it seems like there is a flattening for the intrinsic size around 250 parsec or something like that, which is fairly close to the physical softening that you're using, right?
Yeah, exactly. So our physical softening length is about minus 0.55 on this plot here. So that kind of corresponds really to this, this drop off that we see. It's not so much, not as present in this relation because we are certainly above that for our lower mass galaxies.
Okay.
Yeah.
Okay, so I think it's time to switch to the next speaker then. So the next speaker is Laura Sommovigo. Can you please share your slides?
Yep. Okay. You see my screen?
Yes.
Okay. So I'm gonna start now.
Okay.
Okay. So hi everybody, I'm Laura Sommovigo, and today I will discuss about the cosmic evolution of the dust temperature, myth or reality. So in the last few years, thanks to the advent of submillimeter interferometers such as ALMA, it has been possible for the first time to observe the dust emission from very early galaxies at redshift higher than 7. This has been somewhat surprising, as we have really seen that we have dusty galaxies well into the epoch of reionization. This has left us with several questions open, broadly related to the physical properties of the first generations of galaxies. For instance, what are their dust properties, and particularly their dust temperature? Do these properties evolve with redshift? How do these early galaxies, which are so young, build their metals and dust, and enough dust so that it's observable today? And what is the effect of dust obscuration into the epoch of reionization? So today we will focus on the first question mainly, and this brings us to the title and topic of my talk today, which is the cosmic dust temperature evolution. So what is this cosmic dust temperature evolution? What you are seeing here on the y-axis is the dust temperature, and on the x-axis is the redshift. These purple points that you are seeing here are from recent work by Schreiber, who analyzed the stacked SEDs of low redshift galaxies to intermediate redshift galaxies in the HRS and Candles fields. And he found a very tight correlation between the dust temperature and redshift, claiming that the dust temperature increases linearly with redshift. And this is somewhat consistent with the latest results by the Alpine collaboration presented in Betterman's paper of 2020. So what people have been doing after that is to try to extend this relation into the epoch of reionization by adding the few sources, individual sources that we know the dust temperature, for which we know the dust temperature at very high redshift. And what is interesting and puzzling is that different works have arrived to somewhat clashing conclusions. On one hand, we have the work by Bowens of 2020, who did a fit of exactly the data points that I'm showing you here, and he found a linear relation which is pretty much consistent with the prediction by Schreiber, with a little modification in the slope. On the other hand, Feist and Liang have found a somewhat different relation, with, in particular, a flattening of the evolution of the dust temperature at redshift higher than 4. And in this case, this fit is based on the massive fire simulations. What has really been hindering on an observational side the progress on this matter is the lack of a large amount of data at redshift higher than 5, and the very large errors that affect the few dust temperatures that we have, altogether with a big scatter in these values that we see for very high redshift galaxies. But most of all, there's a sort of an elephant in the room that we are ignoring, which is that there's no physical motivation for any cosmological evolution of the dust temperature. In fact, both of the curves that I'm showing here are fits either to observations or simulations, but they do not rely on a physical modeling. At least for the observational limitations, the recent ALMA large program Rebels can really help us progress further. In fact, Rebels targeted 40 of the brightest galaxies that we knew that we have observed in the UV between redshift 6.5 and 9.5, scanning for the C2 line and O3 line and then the underlying dust continuum. This has allowed us to have the first statistical sample of far-infrared continuum detected galaxies at redshift 7. Unfortunately, all this very interesting data would have been impossible to interpret with traditional SED fitting, as for the continuum detected galaxies, we only have a single data point at 158 micron, meaning that it's impossible to constrain the dust temperature of the sources altogether with their dust mass from the traditional SED fitting. With this common observational limit in mind, we proposed a new method to derive the dust temperature relying on a single observation by combining the C2 information with the underlying dust continuum. So what you see here is the formula that we all use to describe the far-infrared continuum flux. And once that you have fixed a dust model, you are left with your two unknown parameters, the dust temperature and the dust mass. Our idea was mainly to rewrite the dust mass as a product of a dust-to-gas ratio, which scales linearly with the metallicity, and a C2 to total gas conversion factor multiplied by the density luminosity. We then use well-known empirical relations to derive an analytical formula for this alpha C2 conversion factor, which are the Deleuze relation and the Kennicat-Smith relation. So, saying everything in few words, we use the C2 luminosity as a proxy for the dust mass, so that then we can use the single continuum information to constrain the dust temperature. This method has been tested on several local and high-redshift galaxies, and in all cases, we recover the same dust temperature obtained with traditional SED fitting within 1 sigma. Here is a summary plot of our tests. On the y-axis, you see the dust temperature derived from our method, and on the x-axis, that derived from SED fitting. And you can see that in all cases, the data points lay within the area around the bisector plus minus a 30% uncertainty, meaning that our method works really well. So now that we have, among all these sources, I want you to focus on one galaxy in particular, which is ZD1 at redshift 7.15. In fact, this galaxy has recently been reanalyzed in a paper that we have been writing with Tom Bax, and we have presented the first ever, sorry for that. Sorry, the first ever band-name data for such a high-redshift galaxy, meaning that for the first time we are able to scale the peak of our infrared emission, constraining the dust temperature to an unprecedented precision. And it's very encouraging that also in this case, our method gives a consistent result with the traditional SED fitting. So at this point, we go back to the cosmic dust temperature evolution plot, and we focus on the sort of average dust temperature obtained from stacking, and we can add a point corresponding to the average dust temperature that we obtain with our method for Rebels galaxies. This temperature is around 47 Kelvin, and you can see that it lays below the prediction from Schreiber. And it basically sits in between the prediction from the simulations and that from observation, meaning that we cannot rule out either of the two, but also that neither is really describing at best what we are seeing. But we can do something more. We can really look at the individual detections, having an unprecedented large number of data even at high redshift. So we go and unpack the low redshift stacked SEDs into the individual sources. And you can already see that the tight correlation is much less evident. And then we go and add all the individual galaxies on which we can apply our method for the dust temperature derivation. So you see all the Rebels galaxies, and I want you also to note that there's a region where we basically can say that the individually detected alpine galaxies temperatures lay. And in fact, also for these sources, we can apply our method and derive the dust temperature of the individual galaxies. So at this point, we could have simply closed the deal doing a fit of all these data points, but we wanted to do something more and really go at the core of the problem. So the lack of a physical motivation for any trend of the dust temperature with redshift. So we produce a new physical model for the cosmic dust temperature evolution. I have backup slides on the details of the model. But basically, the point is that we are able to connect the dust temperature with the total gas depletion time, which is the total gas mass divided by the star formation rate. And in particular, we see that the dust temperature scales with the inverse of a power of roughly 1/6 of the total gas depletion time. And this is exactly where the dust temperature cosmic evolution comes into play. In fact, we know that the total gas depletion time decreases at higher redshift, meaning that in turn, the dust temperature is going to increase. So in other words, the dust temperature raises mildly as with redshift due to the decreasing total gas depletion time at high redshift. So comparing with the data, this is our prediction, the black curve that you're seeing, and you see that there's a pretty good agreement. But you can also see that the temperatures from data are actually much more scattered around this relation. And this is explained by this additional term in our model, which is dependent on the individual galaxy properties. In fact, you can see that there's a dependence on the optical depth to UV, tau UV, and the metallicity. And this term is exactly responsible for moving this individual relation around at fixed redshift for different galaxy properties. What I'm showing you here with this colored region is our prediction for reasonable values of tau UV and of the metallicity. And we can focus on two approximations, that of UV transparent galaxies with low optical depths and that of UV obscured galaxies. For the UV transparent galaxies, basically this term is equal to the ratio between the optical depth and the metallicity, which is nothing more than the column density of the galaxies. So in this case, at fixed redshift, the only quantity on which the dust temperature depends is the galaxy column density, with larger column densities corresponding to hotter dust temperature. This is straightforward to interpret physically, as larger column density also imply larger optical depths, meaning that you are much more efficiently heating your dust. The other approximation that we can consider is that of UV obscured galaxies. And in this case, basically, the upper term is it's equal to 1. And so the only parameter on which the dust temperature depends is the metallicity, again, at fixed redshift. And in this case, we have that lower metallicities correspond to hotter dust temperatures. This is, again, easy to interpret physically, because lower metal content also means lower dust content. So for a given UV field, it means that you are much more efficiently heating your dust, attaining larger temperatures. What is really interesting of our model is that then we can also pinpoint which are the main characteristics that really distinguish the high-redshift galaxies for which we observe very hot dust temperatures from the ones for which we see very cold dust temperatures. In fact, we predict that the hot galaxies are obscured systems with low metallicity, below 1/3 solar, whereas the colder ones are more transparent systems with column densities around 10 to the 20 centimeters to the -2. So let me now summarize our results. First of all, I've presented you a new method to determine the dust temperature, which is based solely on the 158 micron information, and in particular on combining the C2 line emission used to constrain the dust mass and the 158 micron continuum to constrain the dust temperature. We have applied this method to Rebels galaxies, which are the first statistical sample of very high redshift for infrared continuum detected galaxies. And what we find is that the dust temperature, the average dust temperature for these sources is colder than expected from the previously proposed empirical TD redshift relation. And in fact, we derive a new physical model that motivates the increasing trend, finding that it's milder than linear, and that it depends on the fact that the total gas depletion time over the galaxies is shorter than in local galaxies. Finally, we can also explain the scatter in the observed dust temperature at any redshift, because it is depending on the different optical depths and metallicities of the various galaxies. Thank you for your attention, and I'm happy to take any questions.
Thank you, Laura. So there's a question on Slack. Are all the dust temperatures plotted on TD versus redshift figure using your analytical method?
Yeah, sorry, I forgot to mention this. So this is actually a really important point. That for all the high redshift galaxies, we have consistently applied our method. So we are sure that we are comparing the temperature obtained in a consistent way. So we are comparing intrinsically equivalent quantities. So yeah, it's all the temperatures obtained with our method, which was actually a limitation of some previous works that were basically collecting together data from other different works which had different SCD fittings applied.
We have time for one more question. Here's one from Tom Bax. Does the tight correlation you find between the redshift temperature relation provide some constraints on the apparent UV to infrared offsets or spatial separation seen in, for instance, Bowler 2021? Or are these simply causing a larger scatter along your relation?
So we cannot actually say much of the offset between UV and infrared from this model, because it's a really simple model where we are considering the galaxy as a single blob where you have UV and infrared emission to be cospatial. So we cannot really say anything about that. But we are actually working on a more detailed model with a two-phase model of the ISM where we can actually target also the separation in these two emissions. So not with this model, but we are working on this actually.
Okay, unfortunately, we don't have time for any more questions, but there are more questions on Slack that you can answer in writing.
Thanks.
Okay, so it's time to switch speaker. The next speaker is Jordan Mirocha. So can you please, Jordan, share your slides?
Yes. Okay, so hopefully you're seeing them now.
Yes.
Perfect. All right. Well, thanks to the organizers for giving me the chance to speak today. I'm going to talk about some work that I did mostly last year, though I'll get to some newer stuff at the end. But the topic is really on this question of what galaxy properties, if any, at high redshifts are evolving with redshift, not just things like halo mass or stellar mass. Okay. So in particular, I'm going to focus on the efficiency of star formation, it's, the amount of burstiness that's going on, and the dust content of high redshift galaxies. So the plan's pretty simple, I think, as most people on this call know. Surprisingly simple models of galaxy evolution at high redshifts that adopt a universal or time-independent star formation efficiency do a really good job matching the evolution in UV luminosity functions and colors, which I'll describe in a bit more detail in a moment. But stellar feedback arguments predict that the star formation efficiency should evolve with time. Okay, and in fact, as we've just heard, you might expect some evolution in the dust properties of galaxies as well. So the point of my talk is basically to ask this question, what's going on here? All of these models can't be right. So do we have the tools to distinguish them? So I'll try to convince you that actually to reconcile these more physically motivated models for the star formation efficiency, you require pretty rapid evolution, both in the duty cycle and the dust production efficiency. And so this is a semi-empirical approach. And so toward the end, I'll try to speculate a little bit about the whether or not this inferred evolution lines up with any physical arguments. Okay, so the bad thing is that this is a bit of a fine-tuning problem. These different models can always fit the luminosity functions and colors. And so I hope we have some time to discuss at the end how we might proceed. Okay, so a one-slide primer on semi-empirical modeling, which is the approach I'll take throughout as a review. So these models are sort of calibrated to high redshift observations, traditionally to UV luminosity functions, like I'm showing you on the left, sometimes UV colors as well, or beta. And I'm not going to use stellar mass functions in the FITs, but we do compare to them in the paper if you're curious. And so the key to the semi-empirical approach is that we assume we know a few things like halo mass functions, halo growth rates, and then we parameterize our ignorance. Okay, so in this case, the star formation efficiency, which we define relative to the mass accretion rates of galaxies, and the dust column density or some dust scale length and formation efficiency. And then we run an MCMC, and we try to infer the properties of galaxies that we don't know, like the star formation efficiency. Okay. And so the first step we took in this work is to generalize things a bit and to ask these more physically motivated questions rather than invoking an IRX beta relationship to correct for dust, which is often done. We employed a simple physical model where we basically imagine a galaxy like a point source and a uniform spherical cloud of dust, in which case we can redden the intrinsic spectra of galaxies that are predicted by our model, synthesize their SED, observe them through HST filters, and do a fair comparison to the observations. And so the kind of free parameters here are, the opacity of dust, which we assume is a power law, the dust scale length, which we parameterize, and then we link the amount of dust to a fixed dust formation efficiency, or dust to metal ratio, if you like, FDTMR. And so when we do this, we kind of recover the usual result, which is that a model like this can adequately describe the evolution in the UV luminosity functions, but we also recover the mild evolution observed in UV colors at fixed MUV, which is what's being shown in the right-hand column, despite the fact that none of the parameters in this model evolve with time. So this isn't necessarily a new result, but this is just a setup of what'll come next. Okay, quick aside, feel free to ask me about this later. I think we have a kind of cute explanation for why UV colors and Lyman alpha emitter fractions could both be related to scatter in the dust column density in galaxies, but I don't have time to talk about this now, but there's some details about this in the paper. Okay, so the big question for this talk is whether these universal star formation efficiency models and dust models make sense. Okay. And so the basic argument behind redshift evolution of these quantities is given by stellar feedback arguments. So this is one here where we assume that star formation occurs in a balance between inflow and outflow, and the magnitude of the outflows depends on eta, the so-called mass loading factor. And so if you want to get an idea of what eta should be, you typically assume that star formation will proceed until energy or momentum injected by supernovae explosions is sufficiently high to unbind gas from galaxies, and that gas, of course, would otherwise form stars. And so you find in the energy regulated case, which is what I'm showing here, that you expect actually pretty strong redshift evolution in this quantity, like 1 plus Z. with a mass dependence as well that varies a little bit depending on whether you choose momentum or energy regulation. And so this kind of argument is generally baked into semi-analytic models at some level. And we heard a little bit about this yesterday. So to give you a sense of what this looks like, if you start from a model with constant f star and no dust, and then you just assert that f star evolves like 1 plus z, you get these dashed curves. And so this is visibly noticeable even with a relatively short time baseline between redshifts 4 and 10. So the problem isn't that we've just not had a long enough time baseline to work with. In principle, one should be able to see this. Okay, so a natural explanation to fix this problem might be to say, okay, star formation is bursty, and so only a fraction of galaxies in any MUV bin are on at any given moment. That would help you shift these dashed curves downward. But we also have to worry about getting the colors right. And so naively, you might look at this and say, okay, I need to shift the dash curves to the right, so make galaxies increasingly red as we go to high redshifts, which may not make intuitive sense. However, galaxies are shrinking, okay, as we heard earlier. At least the virial radii of dark matter halos is shrinking. So it's possible that at fixed halo mass, you could have the same amount of dust give you a higher optical depth. But you run into another problem then. If you assert that the kind of dust scale length knows about the virial radius of dark matter halos, and trying to come up with the right colors, you end up dramatically under-predicting the abundance of bright galaxies at high redshifts. Again, that's what's being shown here. Okay, so I'm not the first person to notice this problem. Okay, so like Aaron, for example, has some nice papers that show that in order to kind of avoid this problem, you need something like a redshift-dependent dust opacity. In this work, I'm going to take a slightly more generalized approach, and I'm just going to parameterize flexibly the duty cycle and the dust formation efficiency of galaxies and kind of apply the same semi-empirical machinery to ask the data what these things have to be in order to save these physically motivated stellar feedback models. Okay. And I'm also going to force the dust scale length to know about the halo virulent radius. So once again, these models have 8 or 9 parameters, depending on how you do things. You still can recover the evolution of luminosity functions and colors. There are some mild differences here, though I haven't showed you the confidence intervals just to keep things neat and tidy. But suffice it to say that these all provide pretty accurate description of the data. And the key question, though, is for these energy-regulated models, or momentum-regulated models, the dashed and dotted curves in each panel, how different are these models under the hood from the universal star formation efficiency models? Okay, so of course, the star formation efficiency is the same. We force that to be the case. But then the duty cycle in the middle and the dust to metal ratio on the right, we see evolve rapidly with redshift, okay, going from the solid to the dashed curves. They have a strong mass dependence, though it's less statistically significant. All right, so these trends qualitatively might jive with your intuition. Okay, so the duty cycle is getting lower at high redshifts and in lower mass halos. And so is the dust content of galaxies. But in detail, this is not a physically motivated model. So I think an interesting question is whether physical models predict this kind of behavior as well. I'll come back to that in just a second. But kind of keeping in the kind of empirical spirit of this work, if you want to remain agnostic about what's happening in galaxies and just try to let the data tell you which of these models is right, one thing you might think about looking at is clustering, because fundamentally each of these models is changing the mass to light ratio of galaxies. And so I'm not going to focus on any of these panels in any detail. We're basically taking different halo mass and MUV cuts of the galaxy population to see how much these models differ. And you can see the difference between the solid line, the universal models, and the dotted line, these are the momentum regulated models, are the most different in each panel, though these differences are quite small. Okay, so maybe this is possible in the future if we can measure the typical galaxy bias to 0.1 or 0.2. That's going to be hard. So for the last few slides, I want to be a little bit more speculative. Okay, so my collaborators and I have been thinking about a few aspects of this model in more detail. So we had some nice talks yesterday. I talked about burstiness from Anne and Daniel. I just want to advertise that Steve Furlanetto and I just wrote a paper this summer putting forth an analytic model for stellar feedback that kind of operates in the same framework as the kind of feedback models I introduced earlier. And so the main question we wanted to ask is if we incorporate the fact that there's a delay between star formation and feedback from supernovae explosions, can you predict at what redshift and what halo mass galaxies ought to settle into a more continuous mode of star formation, a less bursty mode of star formation? And so I'll leave the details to the paper, but we found that this transition happens in atomic cooling halos even, so 10 to the 10.5 solar masses or so. Halo masses is about the number you come up with, which is sort of incidentally where current observations lie when you map MUV to halo mass at high redshift. So that's sort of interesting. A little more speculative of a note is, of course, burstiness can come from more than just the delay between star formation and supernovae explosions. So the models on the previous slide ignored radiative feedback, which could start earlier. It ignored fluctuations due to variability in mass inflow rates into galaxies. And so in a different paper, my collaborators and I explored models in which, again, the star formation rate is linked closely to the mass accretion rate of halos, but in an n-body simulation context. And so in this case, we can actually look at how the star formation rates of galaxies change spatially, which we're not able to do in the previous set of models. And what we found is that if you look at the brightest galaxies, for example, in a mock Roman high latitude survey in the bottom row here, the brightest galaxies detected in imaging are not always in the centers of ionized bubbles, which is the color scale here. So the black regions are ionized regions around clusters of galaxies, which you can see more clearly with a deeper JWST wide field like survey in the top row. So this is sort of interesting. In the long term, one could imagine testing this model with 21 centimeter imaging. The field's not there yet, but in principle, one could do this if you found bright galaxies, not in the centers of bubbles, but on the outskirts as well. These are the galaxies in our models that are experiencing very rapid but short-term growth. In the near term, kind of hand-wavy idea, maybe you can do this with Lyman alpha emitters. Okay, you would expect the galaxies detected in imaging in the middle of these bubbles are also Lyman alpha emitters. The bright galaxies detected in imaging on the outskirts are probably not Lyman alpha emitters, more attenuation from the IGM, and so maybe that's a way to test this idea. So on my last slide, I'm contractually obligated to tell you that 21 centimeter is coming. Okay, so those of us in HERA have been working very hard on interpreting the recent wave of limits. This summer, SAZERAC, Josh Dillon gave a talk about the limits, but since then, the theory interpretation paper has been submitted and accepted. And we're really proud of this work. We did 4 independent analyses of the power spectrum limits and are now able to say that the Redshift 8 IGM has to have been heated above the adiabatic limit. And so you can expect in the years to come, kind of analogous limits like this to be improving for the ionization history as well. So I will stop there. I'm a little over time, and I'll be happy to take any questions if you have them. Thanks for your attention.
Thank you, Jordan. We do have time for questions. So here's a question from Aswin. I might have missed the proper context. Were the dust to metal ratios in the most massive halos at redshift 4 reaching unity?
Yeah, so this is, I think, just a normalization problem. I don't really believe the absolute scaling of that relation, but I should think a little bit more. That is what was happening in those plots, but it's degenerate with the normalization of the star formation efficiency and a number of other things. Good eye.
We don't currently have any other questions on Slack. If anybody would like to ask a question live, please raise your hand. There is a question from Julian Munoz. Is there a way to Bayesianly test whether energy or momentum regulation is more right? Regulation?
Yeah, so I did not do any sort of model selection here. I think Julian's right. One could imagine doing that here. And if as the data get better, presumably the JWST, the error bars, especially at the higher redshifts, are going to get much better on these luminosity functions. And so it might be that with sufficiently good data, the rigidity of the feedback models, if you really commit to them, have a hard time explaining the data. So that's something I'd be interested in trying in the future. My sort of by eye model selection in this paper seemed to suggest that we're not there yet. But yeah, certainly we should come back to that in a year or two.
Okay, thank you. We don't have time for any more questions right now. So the next speaker is David Robinson. David, can you please put up your slides?
Great, great. Thank you. And I'd like to thank the organizers so much for organizing this and the opportunity to give this talk. So as Eric said, I'm David Robinson. I'm a third-year PhD student at the University of Michigan. And today I'll be talking to you a bit about a project looking at the cooling and heating functions of simulated galaxies from the Cosmic Reionization on Computers project, which raises the question of whether cooling and heating functions actually exist. And I'll tell you more about why in a bit. And I'd like to thank my collaborators on this project, my advisor, Camille Abestruz, and Nick Mead. So for a bit of an outline, I'm first going to go over some background about cooling and heating functions in general, and then the specific simulations that we used and how they're implemented there. And then I'll tell you about two approaches we looked at to summarize the cooling and heating functions of groups of galaxies. And then I'll show you our main result that those two approaches actually give you different results when you apply them to the same sets of galaxies. And finally, I'll mention some of our conclusions. So to start off with, cooling and heating functions describe how the energy density of a gas cloud here on galactic scales changes with time. And specifically, we're just gonna isolate to the rate of change due purely to radiative processes. And we break that up into two terms. So the first is a heating function term gamma that encodes processes that increase the energy density of the gas. And then a cooling function term lambda that encodes processes that decrease the energy density of the gas. And then, as is typical for collisional processes in astrophysics, we're going to factor out the density squared. And specifically for these purposes, we're going to use the baryon number density. And then the expressions in parentheses are indicating that the cooling and heating functions are definitely going to depend on the temperature of the gas. And in full generality, they really depend on the complete distribution of ionization states and energy levels of the gas particles. And so in practice, what that really means is that they're going to depend, in addition to the temperature, on the density and metallicity of the gas. And they can also depend on the incident radiation field that is shining on the gas. And so that's going to be important in simulations of the epoch of reionization. Now, even in general, you can really compute these cooling and heating functions with a radiative transfer code like cloudy. And you really need, in a sense, need to do that when you have the incident radiation field, because that makes the dependence non-analytic. But of course, even with an incident radiation field, that's way too computationally expensive to do on the fly within a simulation. And I'll tell you a little bit more in a slide or two about how we actually get the cooling and heating functions within the simulation. So the simulations that we worked with in this project are from the Cosmic Reionization on Computers project, and these are hydrodynamic cosmological simulations of the epoch of reionization. And specifically, they go from about redshift 10 to redshift 5. They're too computationally expensive to run above to run to lower redshift, because they're really tracking the ionizing radiation field of the galaxies. And I'll note that these simulations are based on adaptive refinement tree code. So on the left, we have an image of a box from one of the Croc simulations. Galaxies are shown as points in yellow, and then the red is neutral hydrogen and the blue is ionized hydrogen. And so you can see that these simulations are really tracking how the process of reionization occurs. Now, for the purposes of this project, we used a single 20 H inverse co-moving megaparsec box realization of these simulations. And so I mentioned that the simulations track the ionizing radiation field, and then also because they're hydrodynamic simulations, you need to follow the cooling and heating functions. And because we have incident radiation fields, we need to actually approximate how the cooling and heating functions depend on that radiation field. And so specifically, the way that that's done in these simulations is an approximation scheme from Mead and Holland 2012 that uses a lookup table that's constructed from cloudy calculations of full cooling and heating functions. And specifically, the approximation boils down the more complicated dependence to dependence on temperature, density, and metallicity, as you would expect, and then also 4 photoionization rates summarizing the radiation field. And we can get these 4 photoionization rates from the simulation output. And The 4 photoionization rates that we use are the Lyman-Werner band photodissociation rate for molecular hydrogen, and then the photoionization rates for hydrogen-1, helium-1, and carbon-6. Now, I've color-coded these to indicate that the first 3 in purple are UV rates, and that's important because in the simulation, they include both contributions from local stars in the galaxy under consideration, as well as a spatially constant UV background. However, carbon-6 is an X-ray rate, and so within the CROC project, the only contribution there is a spatially homogeneous quasar background. There are no local contributions from the galaxy under consideration. And so just quickly, I want to show you a little bit what this approximation looks like. So here on the top row, we have 3 different radiation fields. And then on the bottom row, we have the cooling functions in blue and the heating functions in red, produced by that radiation field. The solid lines show the cooling and heating functions for solar metallicity, whereas the dashed lines show the case with zero metallicity. And so a couple of things worth noting from this plot are that the radiation field and the form of it can absolutely affect the cooling and heating function. And then the metallicity makes a big difference, especially for the cooling functions. And so applying this approximation, we can apply it to every single gas cell within the simulation. And in doing so, we get a set of cooling and heating rates for each cell. And so a question that naturally arises is if we consider a single galaxy or a group of galaxies, we're going to have an ensemble of cooling and heating rates. And so on the left, I've shown a slice through one galaxy in the simulation. And this is going to be true that we get an ensemble of different cooling and heating rates, even if we limit the range of densities and metallicities. Because the cells have a variety of photoionization rates, we get a variety of cooling and heating rates. So then the question that we were trying to answer is, how can we describe a single set of cooling and heating functions of temperature that could be implemented in, say, a semi-analytic model of galaxy formation that was effectively one zone? So we considered a couple different approaches to that, and I'll tell you about 2 of them. So the first thing that we could do is that we could simply look at, for each cell, we calculate the cooling or heating rate, as I said, and here let me talk specifically about the cooling function. And then at each temperature, to find a summary over the galaxy, we can simply average over every cell that has temperature within some narrow bin around that temperature value. And in so doing, we get a cooling function, and we can do an exactly analogous procedure for the heating function. And so this is great because what this really does is it tracks the true thermodynamics of the galaxy or group of galaxies under consideration, because as time evolves, this procedure will actually track how cells are dynamically evolving as they cool, because we're actually tracking the temperature of each cell. Now, another thing that we could do is note that for all the parameters other than temperature, so the density, metallicity, and photoionization rates, we really have distributions. And I've shown the distribution of photoionization rates, and I'll talk about what goes into this data in a slide or 2. And so we could choose to just characterize all of these distributions simply by their median, as shown in the vertical red lines. And so then to find a cooling or heating function at each temperature for the ensemble of galaxies, we can simply evaluate the full cooling and heating function at that temperature. And then for all the other parameters, we characterize by their median values. And so this is really telling us the cooling or heating function at typical values of the other parameters. And so this is nice because this approach could actually be calculated using a radiative transfer code like Cloudy, given the median density, metallicity, and photoionization rates. And a key thing to note here is that we're actually completely ignoring the temperatures of each cell in this approach. We're not using them at all. So then the main question that we were trying to answer with our results is, do these 2 approaches tell us the same thing? Are they meaningfully different from each other? And the answer, as you might expect, turns out to be yes. So here on this slide, in the dashed blue curves, we're showing the flow line cooling and heating functions, cooling in the top panel, heating in the bottom. And then the green dotted curves are showing the median values curves. Now, to tell you a little bit about the data that goes into this, we're using 50 randomly selected central halos above 10 to the 10 solar mass per H. And then we're limiting the density to between 1 and 10 per cubic centimeter. And the metallicity is limited to between 0.03 and 0.1. And if you're curious later, I can talk a bit about why we choose those ranges. And then the shaded regions are showing the 25th to 75th percentile spread. And so for flow line, that's the 25th to 75th percentile of the rates in each bin. Whereas for median values, we're actually showing the range from looking at the 25th percentile of each parameter rather than the median to the 75th percentile of each parameter. And so the key takeaway from this plot is that these two curves are different. Below 10 to the 4 Kelvin, they're clearly different for both quantitatively for the cooling function, and they even have a qualitatively different shape for the heating function. When you go above about 10 to the 4 Kelvin, the two cooling functions actually agree with each other pretty well, but that's not the case for the heating function. And so sort of the main way we interpret that is that the true thermodynamics given by the flow line cooling and heating functions can't be captured by these median values curves that could be computed from a radiative transfer code like cloudy with typical density, metallicity, and radiation field values. And so that's the main takeaway that we had from this work. Or that the true thermodynamics are captured by the flow line curves, and we simply can't get those from the thing that we could get from a radiative transfer code like cloudy. And with that, thank you for your time, and please let me know if you have any questions.
Thank you, David. So let me remind people that you can either ask questions in Slack, or you can raise your hand if you want to ask a question live.
Hello.
Yeah, go ahead.
Thanks. Thank you very much for the nice presentation. My question is, how is the cooling rate related to the dust properties, say density distribution, and also to the gas properties other than the kinetic temperature? Thank you.
Okay, so in the approximation that we use here, I believe the cooling and heating rates are so they're related both to the gas temperature, and then there are significant effects of the density and metallicity. So I think if I go back to this slide of the approximation itself, you can see that changing the metallicity has a significant effect, and that's kind of expected because when you change the metallicity, you change what cooling and heating pathways are available to the gas, and the density has an effect as well. I believe that in the approximation scheme that we're using, the dust content doesn't actually play into these cooling and heating functions.
Okay, thanks.
So there is at least one more question in Slack, but I think we are kind of sort of out of time. So I suggest you answer that one in writing. Okay, so it's time for the last talk of the session, which is by Will Roper. So Will, can you start sharing your slides?
Would help if I also unmuted and turned my video on probably, but right, yeah. Hello, I'm Will Roper from the University of Sussex. as everyone else has, I'd like to thank the organisers for giving me the chance to give this talk, but also apologise to them for making them try and shoehorn this talk into one of the sessions that they've had planned. It's because in this talk, I'm going to go through a side project I've been working on, which stemmed from sort of observations of the weird behaviour that halo finders can do when detecting structures in hydrodynamical simulations, and how that is does not emulate what observers actually see when they look into the sky. And I want to propose a method to actually improve that, and as the title says, pretend to be an observer, which does come with the big caveat that I'm not an observer. I'm very much a simulator and very much on the development side of that. So do take that into account. Right, so I'm going to start by motivating why this matters. So it shouldn't be a surprise to any of us, but comparisons between simulations and observations are really, really important. So when we simulate things, it's all well and good. We can make beautiful pictures, but we need to make sure that we're actually simulating the real universe. So to do that, we compare to observations. This validates the models we're using, cosmological galaxy evolution models, which you can see in these 3 papers from the flares papers 1, 2, and 3. We can make measurements and comparisons of galaxy properties, both in the real universe and what we see in simulations, to try and validate that. And also, probably most importantly, we actually use comparisons between observations and simulations to calibrate the model parameters that we use. So that's what's shown here in Crane's 2015 paper, where they were calibrating the Eagle subgrid model. So they are important, that is undisputable, but when it's very, very hard to compare like with like. There are fundamental differences between the real universe when we look with a telescope or simulations. And here I'm going to focus on hydrodynamical SPH simulations because it's what I know. But first off, there's different sensitivities involved. So with simulations, we're not only sensitive to the extraction technique, but we're also sensitive to the choices made in the subgrid model, and indeed then post-processing to get fluxes out of the particles, etc. Whereas in the observations, we can't change the physics, but we're sensitive to the extraction techniques and the source modeling that's used. More fundamentally, stars in simulations are the massive particles that represent a massive mass of stars. And this unresolved population is itself a SPH kernel underneath, so it's a smooth distribution. In observations, stars are again unresolved, but these are unresolved stellar populations that are not smoothly distributed. They're decidedly stochastic based on density fluctuations that the galaxy formed from. Again, more fundamentally still, when we're actually looking at galaxies from simulations, we're often doing this in a 3G aperture, which the halo finder or the structure extraction method has decided contains particles it thinks are in a galaxy, and all particles not associated to that galaxy have been removed. So we're looking at these galaxies in isolation. Whereas in observations, these galaxies are viewed in a 2D projection. They can be blended along the line of sight, and they're inherently not isolated. They're out in the real universe. Then in the simulations, we have quote unquote a perfect view. So there is no noise. We have the structure extraction, and our results have knowledge of the faintest structures. And in the observations, you have a maximum survey depth. There is a background which washes out the faintest structure and gives you a limit on what you can actually see. And fundamentally, the extraction techniques are different. For simulations, we use halo finders. For observations, I'm going to focus here on segmentation maps, which are a sort of naive, simple method for extraction of galaxies from images. I know there are more sophisticated ones, but I'm not an observer. So then, beyond that, still, there are further caveats. So in the simulation side, there are multiple different types of halo finders. Each individual halo finder, even if it's of the same type, actually has differences. So my halo finder of choice would be a phase-space halo finder. I'm going to omit those totally here because they, in theory, are very good at actually selecting isolated galaxies because they use the velocity distribution as well, but they are as far from a segmentation map or an observer method as possible. And in fact, the simulations I'm using used density field halo finder. So these, one example of which is Subfind, which is the halo finder used in Eagle illustrious flares. It comes packaged with Gadget. These start with a spatial friends of friends candidate, like host halo group, and then use particle position, mass, and gravitational energy, amongst other intrinsic simulation properties of the particles, to find saddle points within the density field of a group. So you can see the friends of friends group up here in the top left-hand corner. And then this gets split out into a main central galaxy group, so subgroup 1, and then a bunch of other smaller density peaks, which are other galaxies within the group. But there's the downside to these density field approaches is you can often get a spurious splitting where particularly high density peaks are stripped away from the background galaxy that they're definitely connected to, or indeed you get this background fuzz, as it's been called here, where otherwise local particles have been kicked out of a galaxy group because they failed an energy criterion or something like that. They have been deemed not part of that galaxy, but they are local to the galaxy, so they are there. Then on the observer side of things with segmentation maps, these structures are defined based, again, on position, but this time on flux. So they're connected local groups of pixels that are above a certain threshold, either in flux or signal to noise. The background, so the noise, is actually then removed by masking if it's not part of a segment, but you still have a blending problem here. So the blending stages are necessary, and in the work I'm showing here, and what FOTUTILS does, Python package, is it takes a bunch of isodensity levels and a contrast, and then deblends the segments based on that contrast and the isodensity levels. Once you've got this, measurements can be made either using apertures, so cron apertures or curve of growth for sizes, or you can make measurements on the pixels themselves. And as I'll show later on, the results are extremely sensitive to how you handle these the apertures and the masking of local groups in the deblend. So to show this is actually something we should care about, I'm going to propose a method for making synthetic observations. We first want to start as independent of a halo finder as possible. So we're going to extract all particles local to a friends of friends group center. These then get passed into the method that I detailed back in SAZERAC in the summer, which should be on archive soon, hopefully, which takes properties of the stellar particles themselves, so metallicity, mass, and age, takes models for the birth clouds, the initial mass function, nebular emission from cloudy, and the BPAS model, puts them into Stephen Wilkins' code synthobs, and gives us fluxes back, intrinsic fluxes back for those stellar particles. These we then pass to a line of sight code written by Ashwin, one of the SOC, and we propagate these fluxes along the line of sight and calculate the attenuation due to dust in the gas particles along the line of sight. Once we have these attenuated fluxes, we can sort them using a pixel KD tree and smooth them by the underlying SPH kernel of that star particle. Then specific to this work, we use a further code by Stephen Wilkins, Erit Lux, which is a helper function for doing telescope emulation and survey emulation, and apply an instrument-specific PSF and then a survey-specific noise level. Now, all of these, I've done Steve a disservice by not including his GitHub links. All of these are available on GitHub, as Maddie mentioned in her talk. And there is functionality from many, many telescopes. I'm about to focus on Hubble, but there's Euclid, there's Roman, Webb. It's pretty fully featured and will continue to be developed. Then once we have these images, we need a synthetic detection method, but following an observer sort of algorithm. And I put naive here because it is naive, but to do this, we weight and combine all filters rather than the Lyman break. This gives you a detection image from which you can derive a signal to noise map, which you threshold here at signal to noise of 2.5, which gives you the segmentation map. You then run the deblending here with 1% contrast level and 16 ISO density levels, which gives you the blended map from which you can calculate your catalog properties for your galaxies. And just to give an example of what that looks like, this is the data I'm going to be presenting on the next two slides, or the preliminary results from it. There are 5 depth levels, so each row is a different depth. In the middle is the Hubble XDF depth, and then there's 10 times worse, 100 times worse, 10 times better, and then 10 times worse and 100 times worse. Once we've got all these images, we combine them together and you get the segmentation map. The segmentation map is deblended, and then I've just included on the end here the amount of the intrinsic mass distribution that you are seeing at a particular depth. So there's a few things to note here. First is that at realistic depths, we're really not probing a huge amount of the underlying intrinsic mass distribution, but also as the depth improves, the deblending becomes decidedly insane, splitting these objects apart into many, many little pieces. So there's some tweaking to be done there. And as I'll say later, we're going to improve on this greatly. So just some preliminary results quickly. This is a flux histogram of these sources with the halo finder results shown with bars, and then the various depth levels I just talked about plotted over the top of colored lines. This particular example uses a masking method within the aperture where any neighboring pixels that fall within the aperture are replaced by pixels from the source from the opposite side of the source. So this is source extractor's correct method. And using this method of flux measurement, you get a reduction in the maximum flux in the observational catalogues. The galaxies being split apart, even at the realistic depth levels of the XDF, and they're being shifted to the left. Now, this is going to have an effect on the bright end of the luminosity function. And I mean, there is quite clearly a difference between two approaches, even in this naive realization. And then, of course, you get a survey depth limit imposed. So there's a completeness limit, but which is way above the actual simulation's resolution limit. And just to go really far to the other extreme, you can tell photutils to use an aperture method called none, where it doesn't mask any pixels. And in this other extreme, you go really far the other way, and the observational sources include a lot of unrelated flux and are shifted to the right on this diagram, increasing the bright end of the luminosity function. So hopefully those two plots alone, I hope to include more, but I haven't been able to, sort of give the motivation for comparing with observations with apples to apples comparisons, because halo finders, with all the assumption that goes into using them, do not well emulate what we see when we actually look onto the sky. And here, just in summary, I sort of pointed out that halo finders have a place. The theoretical results definitely do have a place, but when we are comparing with observations, we have to take depth effects into account. We have to look at blending and size variations and things like that to actually make sure we are calibrating correctly, comparing the right models and getting the same results out. And just to note the future work, that was a very naive simulators approach to observational detection. In the future, I'll be using the Farmer, which is the Cosmos 2020 pipeline, which went up on archive earlier this week. And then also including phase space halo finder to look how that varies, extending it to low redshift, and produce hopefully a generalized and parallelized tool to allow anyone to just input any simulation data and get a fully emulated synthetic observation out the other end at a particular depth, using a particular instrument of their choice. And hopefully produce light cones and a fully synthetic survey to actually compare to observations as closely as possible. Thank you very much.
Thank you, William. We do have time for about one quick question. So there is a question on Slack from Frederick Davis. Is there an advantage to starting the procedure from a friend-of-friend group rather than all of the star particles within a given volume or a slice of the simulation?
It's a computational one mainly. So there actually does exist an entire different branch of this code which looks at slices of the simulation, one slice at a time. But then you've got to start making decisions about splitting galaxies apart unless you grow these slices and make them uneven in length. You don't want to slice a galaxy in half with your slice. So it just made a bit more sense in the short term to center on friends of friends groups and then use those as the seeds for making these images. I actually think that slicing is the better approach. I just need to work out a method to do it well and without causing systematic effects in the results you get out the end, with galaxies still being half included in one slice and not the other. But yeah, very, very good point. I actually started doing the former, with slices, or in fact cubes of simulation volume.
Okay, thank you, William. There is at least one more question in Slack, but we have entered break time. So it's time for a 15-minute break before the next session, which is on chemical evolution and AGN. So let's get a cup of coffee.
We'll be back in 15 minutes. See you all.
Hi, Aswin. Okay. Hi. Can you hear me? Can you hear me? Yeah.
Yes.
Okay. I'll try to share my screen if it's okay.
Go on.
Can you see the presentation?
Yes.
And also in full screen, right?
Yep.
Yeah, okay, very good. I'll try to switch slide. Okay, it's fine.
Yeah, it works well.
Perfect. Thank you very much.
Yep.
Stop sharing.
I will try to share my presentation as well.
Yep.
Okay, does that appear in full screen mode?
Yes. Yeah, it switches as well. Yeah, just tell, yeah, everyone please tell me how to pronounce your name as well, so I don't actually mess it up.
Jennifer Mead.
Okay. Thanks.
I'm going to try as well.
Yep, go on.
And here you go. That works, right?
Yes. Yeah.
Very good.
It switches to the next slide as well.
Thanks.
Actually, I need to quickly try as well. This first time I'm using Google Slides for presentation, so see if it works. Aswin, can you see my slides?
Yes.
Good. Okay, conference picture. Spoiler.
Hello.
Hi.
Just to check, can we quickly check our tech setup now?
Yep. Go on.
Okay, great. Thank you.
Yes, it's in full screen and it transitions the next one.
Okay, great. Thank you very much.
Could I check too?
Yes.
This is working okay?
Yeah, it works perfect.
Great. Thank you.
Hopefully everyone is back with us. Welcome to the last session of the SIP. It's mostly chemical evolution and studies of AGN we'll be discussing in this session. I'll follow what Eric did in the previous one, where I won't interrupt you unless you go over your 14 minutes now, in your last minute. So if the participants have any questions, it would be preferable to put in the Slack for posterity's sake. And the first talk will be by Jennifer Mead, and she'll be talking about early chemical enrichment of dwarf galaxies in star-by-star cosmological simulations. Jennifer, if you're ready to share your screen. Yep, you can take it from here now. Good luck.
All right, great. Okay, so hi everyone. My name is Jennifer Mead. I am a second-year PhD student at Columbia University. And like Osman mentioned, I will be talking about the work I've been doing for the last year on the early chemical enrichment of dwarf galaxies in a new set of simulations called EOS. So the EOS collaboration is made up of researchers from the University of Chicago, Georgia Tech, MIT, Columbia University, the American Museum of Natural History, Carnegie Observatories, and Concoy Observatory. And as a brief overview of what I'll talk about today, so I will address the key questions and motivations that drive the EOS simulations. I will then introduce the EOS simulations and some interesting preliminary results that we've gotten when comparing to some previous work. And then I will pivot and talk about my own work, discussing the enrichment of the interstellar medium in the dwarf galaxy precursors that we are simulating. So some of the key, broader key questions that are driving the EOS simulations as a whole are whether or not we can identify the signatures of the first stars and their supernovae, and then if we are able to identify those signatures in the metal poor stars of the Milky Way's halo and local group dwarf galaxies. Some of the questions that I am personally more interested in with these simulations is how the distribution of the overall metallicity and individual elements is influenced by different stellar feedback mechanisms, such as core collapse versus pair instability supernovae. And also whether or not we can identify patterns in the spatial and temporal evolution of the enrichment in these halos. So why do we even care about these questions? So dwarf galaxies, having been quenched by reionization, preserve the signatures of the very first stars. And because these dwarf galaxies then went on and got accreted and are now the building blocks of the Milky Way stellar halo, if we can understand the evolution of dwarf galaxies, this will provide insights into our own galaxies' formation, galaxy evolution as a whole, the first stars, and early chemical evolution. Now, there's a small problem in looking at current chemical evolution models in that most of these models generally assume instantaneous homogenization of our stellar yields. And this only allows us to capture the overall broad view of chemical evolution. However, in the last decade or so, observations of dwarf galaxies have shown that there's actually a very complex scatter both within and between galaxies. And also recent simulations have shown that the overall metallicity is not actually a good tracer of how individual elements propagate. And so all of that being said, that kind of just means that we need to begin doing more detailed things, and we need to model individual stellar histories in order to capture the scatter. And this is where EOS comes in. So EOS is a set of high-resolution cosmological hydrodynamic simulations that are run by the ENSO code. It is a 1 co-moving megaparsec box with an 1840 solar mass dark matter resolution and a 1 proper parsec spatial resolution. It also directly ray traces photoionizing and photodissociating radiation. Now, why is EOS unique? For a couple of reasons. So star particles are modeled as individual stars for both POP3 and POP2 stars instead of the typical single stellar populations. EOS also tracks 10 different metal fields, which you can see here, in addition to the overall metallicity. And it also implements a molecular hydrogen self-shielding correction, the importance of which I will get into in a second. Lastly, EOS has two runs. It has a parent stability run and a no parent stability run. So we implement parent stability supernovae for our POP3 stars in the first run, and then we don't in the second run. So it's just core collapse supernovae. So one of the first things that we wanted to do once we started getting data out of our simulation was to compare to previous work. So what you're looking at here is a comparison to the Wise et al. 2012 Birth of the Galaxy simulations, which use the same initial conditions as EOS. So this is a comparison of the cumulative star formation history. And you'll actually notice a couple of odd things right off the bat. First, EOS, which is the dashed lines that you're looking at, the POP3 star formation, which is in red, starts about 50 megayears before the Birth of the Galaxy simulations. And again, because these have the same initial conditions, this is a little bit odd. You'll also notice that we get much higher POP3 star formation than we do in Birth of the Galaxy. And so we're left asking the question, what is the physical reason or the phenomena that is causing these differences? Now, I'm going to show that this is actually the molecular hydrogen self-shielding correction in combination with the fact that we retrace photoionizing and photodissociating radiation. So if we take a step back and we look at the phase plots for the molecular hydrogen fraction versus the photodissociation rate, so we've got EOS on the left and Birth of the Galaxy on the right, you'll actually see that the EOS simulation is producing much higher fractions of the molecular hydrogen at the same photodissociation rate. So I will note that the photodissociation rate in EOS is not including the self-shielding correction. So we're still getting those very high molecular hydrogen fractions. So if we go back to our cumulative star formation rate, really what's happening here is that the molecular hydrogen self-shielding correction is preventing the photodissociation of most of our molecular hydrogen from the Lyman-Werner background radiation. And if you're interested in a discussion on the effects of self-shielding under various conditions, because it is important, the fact that we are directly tracing this photoionization and photodissociation, I recommend that you look at the references that I've listed here. But more importantly, what we were able to do is show that our results are actually comparable to a similar prescription that was used in Skinner and Wise 2020. And they also found that this molecular hydrogen self-shielding correction does cause earlier and increased POP3 star formation. So in all, because our molecular hydrogen is very important for the cooling of primordial clouds, the fact that we have more of it means that we can get more POP3 stars to form, and we can do so earlier in our simulation. So now that we've shown that the star formation results that we're getting are actually not odd, we can then go and look at the metallicity scatter for our POP3 stars, or produced by our POP3 stars, in halos of our simulation. And we do this in 3 dimensions. So first, we look at the spatial distribution by using a radial profile and fractions of the virial radius. We look at the temporal dimension, and we do this by categorizing our halos by the number of previous supernovae that have gone off. The rationale for this being that with each additional previous supernova that we have, we should be getting additional metals in our halo. And then lastly, we again wanted to look at the differences between different feedback mechanisms. So primarily we're looking at parent stability supernovae, which are again in our parent stability run, versus core collapse supernovae, which are the supernovae we have in our no parent stability run. So one of the very first things that we looked at was the fraction of enriched gas at redshift 14 in our simulation. And the fraction of enriched gas, which is shown on the y-axis, is simply the fraction of gas that is enriched above some level of metallicity. We use a log of -4 in solar, simply because that's kind of where we expect POP2 star formation to start to happen. So really we're asking, how much gas is available to do this enriched POP2 star formation. So again, what's plotted on the y-axis, we have our enriched fraction versus the fraction of the virial radius on the x-axis. On the left-hand plot, you'll see halos that have 1 to 3 previous supernovae, or in other words, low numbers of previous supernovae. And then on the right, we have 4 to 6 previous supernovae, so high numbers of previous supernovae. In the red, we have our no parent stability run. In the blue, we have our parent stability run. The lines are just showing you the median values of enriched fractions for those halos, and the shaded regions are the 25th to 75th percentiles. So you'll actually notice a couple of things looking at these plots. First is that our parent stability supernovae, which are in the blue, are driving higher and more extended enrichment than our no parent stability or our core collapse supernovae. And this is probably perhaps to be expected, as parent stability supernovae are much more energetic, as well as, we rip apart the whole star and we're distributing the contents of that entire star into the surrounding medium. Second thing you'll notice is that having more previous supernovae, as you can see on the right-hand plot, also drive higher and more extended enrichment, perhaps to be expected. Now, the enriched fraction is great and all, but that doesn't actually tell you about the amount of gas that you have available for POP2 star formation. So the next thing that we wanted to look at was the total amount of enriched gas versus the total gas mass of the halo. So what you're seeing in the zoom in on the right is in red our parent stability halos in our parent stability run, in this case for the 2 previous supernova case. In blue, we have our no parent stability run. Our circles simply represent halos that have more than 1 solar mass of enriched gas. The triangles are halos that have less than 1 solar mass of enriched gas. And this is just kind of where we expect to maybe be able to form a POP2 star. One of the things that you'll notice first is that there seems to be no pattern between the red points and the blue points. So there's no difference between our parent stability and our core collapse supernovae. So that in and of itself is interesting, given what we saw with the enriched fraction. The other thing that you'll notice is that within a mass spin for some total gas mass in a halo, there's actually quite a bit of scatter, several orders of magnitude, in fact, in the amount of enriched mass that you get. And so this begs the question, is there like some sort of general stochasticity going on here? So what we can do is we can go and look at these plots for 1 through 6 previous supernovae, and you'll notice the same things. At first, there seems to be no pattern between the blue and the red points, or our core collapse and parent stability supernovae. Second, we see a lot of this same scatter within mass spins for total halo mass. And third, you'll actually notice that there doesn't seem to be an increase in the enriched mass as you increase your number of previous supernovae from 1 to 6. We have that same range of enriched mass. But this really just goes to show that the enrichment process is actually extremely heterogeneous. And more interestingly, if we go and look at the 0 previous supernova case, so these are halos that you wouldn't expect to be enriched, there's actually still quite a bit of variability in the amount of enrichment that you get. And this is likely due to external enrichment by neighboring halos that have had supernovae go off. So this then begs the question, is the stochasticity that we're seeing, the heterogeneity, due to external enrichment? So I can't answer that right now. So that's going to bring me to my conclusions. So earlier on in the talk, I showed that the molecular hydrogen self-shielding correction in combination with the fact that we ray trace our photoionizing and photodissociation radiation promotes both earlier and higher cumulative star formation. And then if we then pivot to look at the enrichment, first parent stability supernovae and having more previous supernovae drive higher enrichment fractions to larger fractions of the virial radius. And then lastly, the enrichment process is actually surprisingly heterogeneous. And there's a couple of things in the future that we're planning to look at. First, what is the role of this external enrichment? And then second, what are the environmental factors that affects either the inflow of primordial gas or the outflow of our enriched gas? And then we hope to eventually apply this process to the individual elements that AOS tracks as well. So you should absolutely stay tuned for those results. And I want to thank you for listening. So I'll take questions.
Thank you, Jennifer. There is one question on Slack now. Really nice talk and simulations. I was wondering if you include a Lyman-Werner background in the simulation, and if not, how does the self-shielding correction change the offset of first star formation?
Yeah, there is a Lyman-Werner UV background that is included in the simulation. So the self-shielding correction is correct. So if we go back to the phase diagram. Okay, so this shows the photodissociation rate that you're getting just from the Lyman-Werner background and local sources. And then the self-shielding correction is implemented on top of that.
Okay, I think we might have to answer that the next question on Slack because we're running out of time. Yeah, thank you for your presentation.
Thank you.
Sean, you ready?
Yeah, I'll just get set up.
Yep. Okay, so our next talk is by Sean Barrett. He's going to talk to us about radiation-coupled primordial chemistry in simulations of the first galaxies.
Okay.
Okay.
Thank you. So, hi, I'm Sean. I'm a fourth-year PhD student at the University of Oxford, and yeah, I'm going to talk about my radiation hydrodynamic simulations of the early universe with a chemical network attached. So I'll discuss why chemistry and radiation are important in the early universe, how I've gone about implementing my model, how I've tested that it's doing what I claim it is doing, and I'll show you some early pictures from my simulations. So in the early universe, before any stars are formed, there's no metals. So the only way you can cool gas below about 1000 Kelvin is by forming these primordial coolants, H2 and HD, its deuterated counterpart. So you can see in the figure on the right, the cooling function for these molecules extends well below 1000 Kelvin. And despite there being no metals around this early, there's a surprisingly rich chemistry involved. That is to say, there's lots of reactions. And also, if you're doing a simulation involving multiple stars or multiple galaxies, you have to consider the light from nearby newly formed stars, which can dissociate these molecules and suppress star formation in nearby regions. And it's also important to note that this is a non-equilibrium problem. So the timescales over which chemistry happens is not necessarily anything like the timescales over which the hydrodynamics happened. So you can't assume equilibrium abundances for either H2 or HD. So there's a lot of uncertainty regarding population-free star formation. In particular, we'd like to investigate the cosmological uncertainties, such as the primordial magnetic field, which is very poorly constrained. And yet it can have a huge effect on smaller objects. So as you see in the figure on the right, there's a large enhancement of the primordial matter power spectrum between 10 to the 7 and 10 to the 8, which have a big effect on dwarf galaxies and the formation of stars within them. And a streaming velocity between baryons and dark matter also has an effect on similar scales. However, it's very difficult to decouple these effects with your star formation prescription or your thermochemical modeling in the simulation. So in order to investigate these with numerical simulations, you have to consider the two at the same time. You can't consider their effects independently and linearly add them. They're too tightly coupled and nonlinear. So it's really important to have a model of chemistry if you want to investigate these. So I've implemented my model by modifying the radiation hydrodynamics code Ramses-RT using some software called Chrome, which takes a list of chemical reactions, such as mine on the right, and generates Fortran code to solve the associated system of ODEs. And I'd like to draw particular attention to the reactions involving gammas with subscripts. These represent photons, photons from each energy bin of Ramses-RT's radiative transfer solver. So photons of various energies are coupled directly to the chemistry in this way. So to test that it's doing what it should, so that attaching a network to the hydrodynamics in this way is a numerically valid thing to do, I compare to work done by Omikai and others on protostellar collapse. So they attach a similar network to mine to a single cell model, which follows a power law collapse. So the density goes as a power law, and they simulate how the chemistry evolves as the collapse happens. And they plot the temperature versus the density here on this figure for various metallicities. So I'm only interested in the zero metallicity case, which is the solid line at the top. and only down to densities of about 10 to the 5, because I won't resolve any higher in my simulations. So ideally, by attaching my network to a 3D simulation, I'd achieve a similar curve. So this is what I tried to do. I've used my network with an idealized collapse and plotted the result in the dashed line there, and then used the same network, same cooling physics with a 3D hydrodynamic simulation to check that it at least gets close. And it pleasingly does, certainly within the tolerance of the large uncertainty of chemical reaction rates. This is more than acceptable. So we can say that the collapse is chemically resolved down to the densities we actually resolve in our simulation, which is good. So what I'm going to do with the code, now that it's hopefully working, is simulate a suite of dwarf galaxies, which we'll use to investigate cosmological effects on population 3 star formation, such as various values of the PMF and a stream velocity beam baryons and dark matter. So in addition to my non-equilibrium model of chemistry, we include models of population 3 star formation and population 2 star formation. So not just the first generation of stars, but the stars that form in the subsequently enriched gas, and supernovae and radiative feedback. So we don't just simulate the first stars and the first galaxies, but also their evolution down to lower redshift in a self-consistent way. So the first stars influence the environment in which the second and third generations of stars form. And very happy to finally be able to show you pictures from this code. So you can see the density temperature here at redshift 13, but also the H2 density and the densities of the intermediate species like H-, which are often ignored in this sort of simulation. We track the H- in a non-equilibrium way, which is new. And I want to emphasize how important it is to do radiative transfer simulations here. So on the right, we've got the temperature and the H2 density before the first stars form, and in the snapshot immediately after. So you can see the gas around the first stars is heated, and the H2 is destroyed. So the environment in which new stars will have to form after these is massively changed. And you can also see the ionization is simulated in the code there. So to wrap it up, my code is uniquely well posed to investigate various things about population 3 star formation, and in particular, we're going to look at the cosmological effects like the primordial magnetic field and a stream velocity between baryons and dark matter. And because we do chemistry coupled to the radiative transfer, we self-consistently capture the effect the first generation of stars and subsequent generations have on their environment. So we can hopefully predict their observable properties down to even lower redshift. And I'll take questions now. Thank you.
Thank you, Sean. I think we have plenty of time for questions.
Yeah.
Okay, so we have a question from Rahul. He's asking, how do you account for the H2 self-shielding?
So I use the, if you're familiar with it, the prescription of Sarah Nickerson, who published a paper about this in 2018. For those who aren't, they essentially say that the Lyman-Werner absorption is enhanced by about 400 times compared to the absorption in other bands. But yeah, the absorption by H2, I mean. So that leads to multiple cells of H2 being able to shield themselves quite effectively.
Okay, thank you. We have another question from Mihir. He's asking, do you expect the effects from baryon, dark matter streaming, and magnetic fields to interact in a non-trivial way? If so, why?
So because we're simulating quite small objects, I would hope that if there's sorry, let me show you. If there's an enhancement of, say, look at the blue line at, masses between 10 to the 7 and 10 to the 8, if there's such a large enhancement at that mass range, that there should be a non-trivial effect on objects in that mass range. And similarly for the baryon dark matter streaming, there's a mass where the effect is quite large, I believe. But we'll see this in the results, hopefully.
Anybody? Oh, yes. So Rahul has a follow-up question. He says, this factor of 400 was derived using a relatively simple chemical network. Does it remain the same even with this more complicated network?
I think that it's almost a resolution dependent effect, but it's something something you can calibrate against other self-shielding prescriptions in photoionization tests. But it seems to work quite well for me. Yeah.
Okay. Does anybody have any other questions? We do have quite a lot of time left.
Okay.
Even if anybody wants to ask a live question, I think the floor is open.
Okay. Sorry, I didn't want to risk going over time.
No, it's perfectly fine. So maybe I could ask a question. So since it's a dwarf galaxy simulation, do you account for like radiation that comes from outside your field?
Not in this one. It's something I could do in other simulations, but this is an isolated object. This one in particular.
Okay, maybe you could say something about like, okay, we have another question from hi Sean, very nice talk. Which photochemical reactions are you including in your network?
So they're all listed here. There's a few extra reactions involved with the formation of HD, but these are all the photochemistry. So ionization of hydrogen and helium, and dissociation of H2 and dissociation of ionized H2, and emissive recombinations too as well.
Okay. Thanks, Sean. I think we'll move on to the next speaker now.
Okay, thank you.
Fabio, are you ready?
Yeah, I'll start sharing my screen.
Okay, good. Wait a minute or so.
Yeah, sure. Just just tell me when I can start.
Okay, our next speaker is Fabio Di Mascia. He will be talking about AGN imprints of the infrared emission of Redshift 6 galaxies and their dust properties. Fabio, you can take it from here.
Okay, thank you very much. So, hello everybody, I'm Fabio Di Mascia, and in this talk I would like to discuss with you about AGN imprints on the infrared emission of Redshift galaxies and their dust properties. So, there has been a lot of progress on the observational side regarding the first quasars in the universe. We know so far more than 300 of them in the first gigayear of the universe. And this is thanks to several sky surveys in the optical and near infrared. And a follow-up from this observation, particularly with spectroscopic follow-up, we were also able to estimate the black hole masses powering this bright object, in particular using the correlation with the magnesium 2-line emission. And the results were quite astonishing because we found that these bright quasars are powered by black holes with masses of the order of 10 to the 8 up to 10 to the 10 solar masses. And then in the latest years, also ALMA was able to probe the interstellar medium on the host galaxies. And this is thanks to far infrared lines like C+, CO, and also the underlying dust continuum. And this observation allowed also to have an estimate of the dust masses in this object that were estimated of the order of 10 to the 7, 10 to the 8 solar masses. So these two interesting observational results also poses a couple of questions, in particular questions regarding the timescale for the process involved. In fact, if we consider the masses of the observed black quasars at Redshift 6, so within the first gigayear, we know that this is of the order of 10 to the 8 and to the 9 solar masses. However, it is quite difficult to explain such an amount of mass by assuming, for example, standard stellar seeds and also Eddington limited accretion. So maybe a different seeding mechanism or a particular accretion history is necessary in order to explain these objects. So the main time problem in this case is the fact that it is quite difficult to have such a huge amount of mass for a black hole at Redshift 6. The second problem regards the dust mass. In the local universe, we know that AGB stars are the main sources of dust production, but in order for a star to go into the AGB phase, it is necessary almost hundreds of mega years, so a time that is comparable with the age of the universe at Redshift 6. And for this reason, supernovae also have been proposed as a mechanism to form dust at high redshift. However, the question here is how much dust actually survives the shock after a supernova. So the second problem that we have regarding time is the production of dust. It is quite difficult to produce 10 to the 8 solar mass of dust within 1 gigayear. So in the first part of the talk, I will focus on the first problem and how we can solve them. We can address this problem by looking at the progenitors of the supermassive black hole that we see. And so is there a way to detect more of them and to learn more about the origin of the supermassive black holes? So we adopted a cosmological simulation in order to address this problem. We considered the suite by Barrett collaborators in 2018, in which an overdensity of the universe corresponding to an halo of 10 to the 12 solar masses is followed from cosmological condition down to Redshift 6. These simulations are carried with Gadget 3, with standard prescription for stellar physics, and an additional prescription for black hole seeding and growth that correctly form a black hole of 10 to the 9 solar masses at Redshift 6. We then also wanted to infer observational prediction from this object. And so we performed the radiative transfer calculation with the code SCIRT. So we focused on a particular interesting snapshot. And here you can see the gas distribution. Then for the radiative transfer setup, we have to infer the dust component because dust is not explicitly followed in the simulation. So we assume a uniform dust to matter ratio, and dust property is typical either of the SMC or Milky Way. We then, of course, include stellar radiation. Here you can see the surface ray density, star formation ray density. And then we also include IGN radiation with power law emission. And also setting the bolometric luminosity proportional to the accretion rate of the black holes in order to be consistent with hadronic simulations. Here you can have an example of how this snapshot of most massive halo look like. On the left, you can see the UV emission, and on the right, the far infrared emission. And the first thing that you can notice is that there is one bright object in the UV and several objects bright in the infrared. And I don't have much time to go into detail about this, but this object is emerging a GN system that would actually appear as a quasar plus an SMG companion, which is something peculiar but also consistent with recent observation. Here I'm showing, for example, the one by the Carlin collaborators of 2017, in which in a sample of 20 quasars, 4 of them were found to have a sub-millimeter galaxy companion. So, but the main point that I want to make here is the fact that it is possible to have AGN that are completely dust obscured, and they would only be revealed as a sub-millimeter galaxy companion. So, can we actually detect them? And in order to do so, we consider the spectral energy distribution, and in particular, I'm showing here the spectral energy distribution for 3 of the runs performed in the suite that we were analyzing. The first run is a control run in which AGN radiation is not included, and it is corresponds to the blue line. Another run is the red one corresponds to bright AGN, whereas the green line indicates the case for a faint AGN. We then look at mid-infrared and far-infrared emissions in the 3 cases, and we found that the ratio far-infrared to mid-infrared is of the order of 100-1000 for the case for the simulation without AGN radiation. When we consider a faint AGN, the ratio drops to 10, and if we consider a bright AGN, the ratio goes down to 1. So the clear effect of the AGN radiation in our simulation is this boost in the mid-infrared flux. So, as a consequence, if we exploit the synergy between ALMA, so observation in the far infrared, and observation in the near infrared, like with the WST or the proposed origin mission, it will be possible to unveil faint and/or dust-obscured AGN. I will move now to the second timescale problem, the one regarding the dust mass content in the quasar host. And we know, as I mentioned in the introduction, supernovae and AGB stars are possible candidates for dust production, but the dust composition resulting for this process is different. So maybe we can look at specific signatures of dust in high-redshift quasars. And something similar has also been done in many other studies. I'm showing here 2 in particular, the one by Madeline and collaborators 2004, in which the extinction curve of a redshift 6 quasar is found to be consistent with dust from supernova origin, and another work by Gallerani and collaborators in 2010, in which a sample of redshift or quasar between redshift 4 and 6 was found to have, on average, an extinction curve flatter than the SMC. So maybe also these observational studies indicate a possible different dust composition at high redshift with respect to the local universe. So we try to use our simulation in order to address these questions. We considered a large sample of quasar at redshift 6 and their multi-wavelength observations, so spectra, near infrared, mid infrared, and far infrared data corresponds to the gray points and lines for the spectra, and we compared with our predicted spectral energy distributions. We rebinned the observations, and then we performed the chi-square analysis by considering several different setups in radiative transfer. In particular, we allowed to vary for the grain size distribution by adopting a cut at lower for the grains with smaller size. And what we find is that 5 models are favored by this analysis, but all of them have a cut in the grain size distribution at 0.1 micron. So all of them lack small grains. As a consequence, you see that the SED in the far UV is essentially flat. And this is due to the fact that also the attenuation curve that we predict, which is shown in the left-hand side panel, it corresponds to the solid grain line. Also, the attenuation curve that we predict is flat, and it is the one required in order to match the optical UV data. You can see that it's also quite flat with respect to the SMC one, but it is also consistent with the one predicted by Gallerani and collaborators in 2010. And what is interesting, so it's to look at the far UV, and we also plan to study extinction curve from a resolution X-filter spectra in the X-Quart30 project. So stay tuned for more results in the future regarding this topic. And on the observational side, we also have soon JWST that will provide high resolution spectra. And this will also be very important in order to shed light on the dust origin at high redshift, thanks to looking directly at the extinction curve in more and more objects. So I will summarize the main results, so the main point of my talk. We show how, by using the mid-infrared and far-infrared observation, the mid-infrared and far-infrared ratio, and so the corresponding facilities, the synergy between the corresponding facilities, we might be able to unveil fainter dust skewed AGN. Then we also fit the multi-wavelength data of high-redshift quasars, and we find that in order to match the observation, we need to assume the absence of small grains, and as a consequence, the attenuation curve that we predict are essentially flat. And in the future, thanks to current and future facilities, we will gain more and more data and information that will probably help us to solve these two timescale problems, the one regarding the black hole mass and the one regarding the dust mass in high redshift quasars. And this is my conclusion. Thank you very much for your attention. I'd be happy to take your questions here or on Slack. Feel free to reach me.
Thanks, Fabio. I think we have time for a few questions. None have appeared on Slack yet. Okay, so Andrea has a question, has a live question, I think. Feel
yes,
free
if I
to...
may, nice talk. Hi. You mentioned the problem to produce dust, and hence the possibility that this dust is produced in some other ways, right? It could be supernovae.
Yes.
But then when you're doing your study, you use the dust to gas ratio from the Milky Way and the SMC, which most likely the dust there is produced in a more standard way. So how do you reconcile these two issues?
Yeah, actually the dust to matter ratio is a free parameter in our model. So we actually changed that, and we used a range that corresponds both to the Milky range from a small value like less than 0.1 for that is more reasonable for high redshift sources, to 0.3, which is more similar to the Milky Way one. And actually, the models that better fit the data are somewhere in between, more toward the 0.15 for the dust to matter ratio.
So if I can follow up, how much your results do depend then on the dust to matter ratio that you use?
Okay, thank you. With the main problem that we find is that when we use an high dust to matter ratio, the attenuation in the UV becomes very high, and therefore we underpredict the UV data. So the results are a bit sensitive to the dust to matter ratio, but are even more sensitive to the actual data distribution.
Thank you very much.
Oh, you're welcome.
We have a question from Tom Bax. He's asking, we find higher dust temperatures can explain higher redshift dust masses. However, larger grains are associated with colder dust. Is the dust budget crisis thus still very much alive for these high Z quasars?
I'm not sure if I understood the questions, but yeah, that's a good point. If we assume higher dust temperature and therefore lower dust masses, then this might in some way help and maybe not require too much I don't know. I think that regarding the dust mass content, maybe this can like not make AGB so unlikely to form the huge amount of dust in this object, because the dust mass will be lowered. But regarding the extinction curve, I think that the main results that they need to be flat in order to match observations, I will say that it stays true.
Yeah, feel free to look at that question again.
Yeah,
and
sure.
Elaborate on it. Yeah, I think we need to move on to our next speaker.
Okay.
Thank you, Fabio.
Thank you.
Sophie, you ready?
Yep.
Yeah. Okay, our next speaker is Sophie Koudmani. She'll be talking about the role of AGN feedback in high-redshift dwarf galaxies. Sophie, the floor is yours.
Thank you very much. And also thanks to all of the organizers for giving me the opportunity to present my research today. So yeah, I'm Sophie Koudmani, and today I'm going to tell you about the role of AGN feedback in high-redshift dwarf galaxies. And yeah, at the moment, I'm a junior research fellow at Cambridge at St. Catherine's College, and this work is done together in collaboration with Deborah Zizachki, Nick Hendon, Martin Bourne, and Matthew Smith. So we've already heard quite a bit about feedback in galaxy formation during this conference, so just a quick recap here. So feedback in galaxy formation is usually invoked to explain the mismatch between the galaxy mass function inferred from dark matter only simulations, which you can see here as the gray line, and the observed galaxy stellar mass function, which you can see here as the black line. And in the common theoretical model, it is then assumed that supernova feedback mainly regulates the low mass end, whilst AGN feedback is responsible for suppressing the high mass end. However, this model has been partly called into question by the mounting observational evidence that at least some dwarf galaxies host AGN as well, so that AGN activity might also play a role here in the low mass regime. And here I've collated some highlights from these observational studies. So the first large samples of dwarf galaxies with AGN were sampled via systematic searches of SDSS combined with X-ray follow-up observations. And by now, there are also many resolved kinematical studies, for example, with MANGA or KEK, which have found evidence of disturbed gas kinematics, as well as direct detections of ionized gas outflows for dwarf galaxies hosting AGN. And the search for AGN in dwarfs is now also being pushed to higher redshifts, for example, in the cosmos field, where X-ray AGN and radio AGN have been detected out to redshifts 2 to 3. And these tantalizing observational hints at AGN in dwarfs have motivated theorists to investigate this largely unexplored regime. And this is a very exciting opportunity because it allows us to stress test our AGN feedback models in a completely new mass regime and to model the interaction between supernova feedback and AGN feedback in more detail, as stellar feedback channels and AGN feedback channels are both likely playing a role in this mass regime. And analytical models of AGN feedback in dwarfs actually look quite promising and suggest that AGN feedback could be an alternative and possibly more successful source of negative feedback in dwarf galaxies, as you can see here in this plot on the right-hand side. But numerical simulations have also found an important caveat, which is that strong supernova feedback can hinder the growth of the black hole and thereby suppress the efficiency of the AGN. However, if the black holes are able to grow efficiently in numerical simulations, then they are found to be able to quench star formation. First of all, I investigated AGN feedback in dwarfs of simulations using isolated simulations, so non-cosmological simulations of disk galaxies with stellar masses of approximately 2 × 10⁹ and a black hole of 10⁵. And here you can see a movie showing you a subset of the simulation suite. In the top row, you've got density. In the second row, you've got temperature, and in the final row, you've got the vertical velocity. And here in the first column, we've got a run without any feedback, so not much is happening. You just have an edge-on view of the disk. Then in the second column, when you add in supernova feedback, you can see the nice large-scale outflows that form. And the last three columns are different AGN feedback models on top of that supernova feedback. And what we can see is that in all cases explored here, the outflows are significantly hotter and significantly faster with added AGN feedback. Nevertheless, we found that actually there was not a significant impact on star formation when adding an AGN on top of supernova feedback. So we concluded that if anything, AGN might play an indirect role in quenching star formation dwarf galaxies. So for example, these powerful outflows might be able to hinder cosmic gas inflows and then essentially regulate star formation in a maintenance mode type fashion. However, we cannot test this with this setup as we don't have a cosmological environment here. So this is then why for my second paper, I moved on to investigate AGN feedback in low-mass galaxies with the cosmological simulation suite Fable. And we found that here, with this cosmological simulation, still low-mass galaxies with above average black hole growth have hotter and faster outflows throughout cosmic time. So confirming the findings from the isolated simulation. We also found that at high redshifts, where AGN activity increases, the AGN is able to contribute to the suppression of star formation in low-mass galaxies. Interestingly, we also found that dwarf galaxies with bright AGN are underproduced at low redshifts compared to constraints from X-ray observations of dwarf galaxies. So this then points to an important caveat when just using off-the-shelf cosmological simulations, which is that to study AGN feedback in dwarf galaxies, which is that, of course, all of these cosmological or most cosmological simulations have been tuned so that supernova feedback is able to regulate star formation at the low mass end. And another important caveat is the Bondi prescription, which I'll go into more detail later. So as I just discussed, the galaxy formation model has a crucial impact on the efficiency of AGN feedback at the low mass end. So I ran a suite of zoom-in simulations, which is currently still in progress, to explore this more systematically. So these zoom-in simulations build on the Fable galaxy formation model. In fact, the first run that we've got here, the strong supernova feedback, is the fiducial Fable setup. So here we assume a high energy wind fraction, as well as efficient coupling with the ISM. We then also have an alternative run where we trial a more realistic supernova feedback parametrization. And the aim is now to see whether this more moderate supernova feedback in tandem with AGN feedback can have the same quenching success as the strong supernova feedback. And to assess this, we use two strategies to reach this high AGN accretion regime. Firstly, increasing the boost factor alpha in the Bondi rate, which was originally introduced to account for the unresolved nature of the multi-phase ISM. Here we just use it as a cheap tool to reach high accretion rates. And the other tool is then similar to the isolated case. We employ constant high Eddington fractions based on the black hole sigmas. So here you can see the cosmic evolution of star formation. On the left-hand side, we've got the star formation rates in these dwarf galaxies as a function of cosmic time. And on the left-hand side, we've got the galaxy masses. So the solid lines show you the stellar mass, and the dashed lines show you the gas mass, again, as a function of cosmic time. And here we're first focusing only on the supernova only run. So dark blue is the strong supernova feedback from the fiducial Fable model. And the light blue line is the more moderated supernova feedback. And we now add an AGN on top of this at redshift 4. And what you can see here is that the fiducial Bondi model from Fable actually makes no difference in the star formation rates. And we need to increase this boost factor alpha from the accretion rate prescription from the fiducial value of 10 to the 2 to 10 to the 3. But if we do that, then the impact is extremely dramatic. So you can see that the star formation is quenched completely, the gas mass is heavily reduced, and this then also results in a complete suppression of the stellar mass, and we have then a similar final stellar mass to the strong supernova feedback run. We also tried an alternative setup where we seeded even earlier at redshift 6 with an even lighter seed. But now the penalty from this black hole mass squared factor in the Bondi rate, which suppresses the growth of low mass black holes, is even more severe, so that in turn, the alpha factor needs to be increased to 10 to the 4 to have any kind of effect. But then again, once we do have an effect, the effect is very dramatic. But of course, with boost factors in the range of 10 to the 3 to 10 to the 4, these are really more numerical experiments rather than within the framework of the Bondi model. And here I'm also showing you the evolution of the black hole mass, as well as of the Eddington fraction, again, as a function of cosmic time. I've split up the late seeding and the early seeding for the Eddington fraction for clarity. I don't have time to discuss the slide in detail, but one thing that I would like to point out is that the efficient run, so here the Bondi boost run and the Bondi extra boost run, actually only have a few high Eddington peaks and then get self-regulated essentially by the expelling of the gas. So it is actually quite remarkable that these a handful of high Eddington accretion episodes can have such a severe impact on the system. And this piqued our interest, so we decided to investigate this more systematically with fixed Eddington accretion bursts. So this time we restrict ourselves to seeding at redshift 4 with the seed mass of 10 to the 4 solar masses. And then we'll try different burst intensities. So 100% of the Eddington rate and 50% of the Eddington rate, and different burst durations. So long bursts of 100 megayears, short bursts of 25 megayears, as well as 2 very short bursts in quick succession of 10 megayears. And we find that there's a suppression of the star formation rate and gas masses in accordance with the burst duration and intensity. And we also checked the overall energy injected by these bursts and found that for the bursts to be efficient, they need to exceed the gas binding energy at the time of seeding. And to investigate a bit more closely how the star formation is actually regulated in these dwarfs, we also looked at the outflow rates and the inflow rates here as a function of redshift. And again, here, the light red shaded and the dark red shaded regions show you the burst duration. So here, the light red shaded is 100 megayears and the dark red shade is 25 megayears. And we can see that even long after the AGN has switched off, the outflow rates are still enhanced compared to the supernova only runs, but even more dramatically, the inflow rates are significantly reduced, in some cases even until redshift 2. So the AGN then efficiently operates via expelling the gas and then cutting off the gas inflow so that there is no more fresh gas supply, and shutting off star formation in that way. And another interesting point to note is that this is especially impactful at high redshifts, because as we move to lower redshifts, supernova feedback itself becomes more efficient at suppressing cosmological inflows, so that the AGN can be especially impactful here in the high redshift regime. And this brings me to my conclusions. We analyzed the impact of AGN feedback on dwarf galaxies using isolated simulations, the cosmological simulation seed Fable, and cosmological zoom-in simulations. We found that AGN drive higher outflow velocities and temperatures and can have a significant impact on gas fractions. And we also identified a parameter space where AGN feedback can efficiently suppress star formation in dwarfs. And it will now be imperative to harness these upcoming state-of-the-art observations, which, for example, JWST, MUSE, the Next Generation VLA, Athena, LINX, and LISA, which were also discussed in detail during this conference, as these will be able to constrain the different theoretical possibilities and allow us to elucidate the role of AGN and dwarfs. Thank you very much.
Thanks, Sophie. We've run out of time, so you probably would have to take all your questions on Slack. Please do answer them.
Thanks.
Okay, so our last speaker of the SIP is Julian Munoz. Julian, are you ready? Yes. So Julian will talk to us about the first galaxies in 21 centimeter simulations. Okay, take it from here, Julian.
Thanks. Yeah, so I'm Julian. I'm a Clay Fellow at the CFA. And I'll tell you about this paper that we just put on the archive appeared last night with all these great folks. And it's about the first galaxies in 21 centimeter simulations. And since there's a short talk, I'm gonna go straight to the punchline, which is that we enhanced 21 CMFAST, the public code, to track POP3 stars in molecular cooling halos with self-consistent feedback. And if you want the even shorter punchline, is that we were able to create a model, which we call all galaxies, which is our best guess model of 21 centimeter cosmic dawn and reionization, that upgrades the all faint and bright galaxies fiducial models that were used for, say, Hera, SKA forecasting. And the question I'm going to ask, we put a lot of great talk in the SIP. Since I'm the last speaker, I get the privilege of telling you a little bit about all of them. So the question I'm going to ask is, what can 21 centimeter do for galaxies? So for example, today, Jordan told us about the star to halo mass ratio and star formation rate of galaxies and how that may evolve or not with redshift. And it has some shape that looks something like this. And we heard from Sophie like 2 minutes ago about how AGN feedback plays a role at high masses and may even play a role at lower masses. But we know there's other processes that also shape this curve, like supernovae, stellar winds, reionization feedback. And the question that I want to ask is, what's happening here? What's happening at low halo masses and high redshifts? And observationally, the best way to try to tackle these questions is to use 21 centimeter, since that is the observable that will more readily be able to see these tiny galaxies. And of course, modeling this is very complicated. So we turn to semi-numeric simulations, which I'll describe in a little bit. But the idea is to be able to resolve down to the first galaxies that cool through molecular lines. And these molecular cooling galaxies, or MCGs, in addition to having all the source of feedback that we've heard in this conference, they also suffer from stream velocities, from dark matter baryon relative velocities, and Lyman-Werner that further dissociate molecules of hydrogen. And finally, we have joint hydrosimulations by these two groups that address how these sources of feedback interact with each other. And turns out that the solution is that they actually add onto each other, so they make feedback stronger. So we added this into 21 CMFAST, but let me describe this feedback a little bit. So the first is Lyman-Werner feedback, which is just to say that photons in the Lyman-Werner band dissociate molecules of hydrogen, so make it harder to cool from molecular transitions. And there is a slice from the shower simulations, and look at these papers that have very similar results, where the top panels are gas densities, which are the same in these cases. But from left to right, you crank up the intensity of Lyman-Werner. So here it's 0, here's 10 to minus 2, here's 10 to minus 1. And the bottom panel is the H2 abundance. So you start seeing how cranking up the Lyman-Werner reduces the abundance of molecular hydrogen, so makes it harder to cool gas into stars. The second effect is the baryon dark matter streaming velocities, which were pointed out in 2010 by Dmitry Selyakovich and Chris Hirata. And immediately, different groups did simulations of how they affect the first galaxies. So in this paper in 2010, they showed that if you have a dark matter halo, because you need the baryons to collapse into it to form the stars, if these two objects, dark matter and baryons, have large velocities, they will just not collapse as efficiently. So when you have no relative velocity, the gas is very dense at the center. You can see here in red. As you increase the velocity, here's pointing rightwards in the slice, the gas starts to stream out of the galaxy, and for very large velocity, it pretty much all streams out. So these two effects basically impede small mass galaxies from forming stars. And we take a very simple model where it's a semi-analytic model of the first galaxies where we implement these effects. So in our 21C and fast simulations, we do not keep track of metallicity for now, at least. So we just say that there's POP3 stars forming in the first galaxies, POP2 in the later generations, and we put the cutoff at the atomic cooling threshold. So again, this is a simple model for now, and it can be updated. And we heard from Jennifer and Sean earlier today about POP3 stars and enrichment. But again, the model we take is much more simple and phenomenological because we want to explore parameter space and large volumes. So I'm going to show you now how these thresholds for forming stars, so the turnover mass to form galaxies to molecular transitions or atomic transitions, evolve with feedback. And the first, we're going to add them one at a time. So the first is Lyman-Werner. It doesn't do anything at high redshifts because there's no feedback yet. And as you form more galaxies, the flux starts to grow and grow and makes it harder to form stars. The relative velocities do the opposite. They affect more at higher redshifts. Since their velocity, they redshift away as the universe expands. And when you join them with the newest prescriptions, including self-shielding and so on, you get this dotted black line. So this is about a factor of 10 or even 100 larger than if you didn't have these effects. And finally, you can include photoheating from reionization, which matters at low redshifts, and you get these solid lines. So these are the minimum masses that galaxies need to form stars. And again, we take a simple model where there's POP3 stars, POP2, each of them has their own parameters that we can vary. And we go and predict the 21 centimeter signal to try to learn from the signal about the galaxies. I'm going to show you an animation of what our evolution of the 21 centimeter structure looks like. And you can go on like this website or any of our collaborators to look at the animations, at the data, download the live cones if you want to play with that. But I'm going to start with the simulation. I'm going to first tell you what the panels are. On the left is going to be a slice of the simulation. The top right is the power spectrum in 21 centimeter, and the bottom right is the global signal. So as it starts evolving, you start seeing how the global signal goes down. That's because of the Woodhouse field effect. The signal becomes blue. Then you start seeing it turning to red. As X-ray heating, it starts to heat up the gas. Then all turns red. Then you see the white, which are the bubbles of reionization, as you start to dissociate all the hydrogen. So this is an animation of this whole process. But if you look at one particular redshift, you can see why we did this, which is to be able to resolve huge scales. So in the first talk of the conference, Rahul told us about hydrodynamical simulations, the Thiessen simulations, which are about 100 megaparsec in volume. And these have very rich physics, but they're much smaller in volume because of the computational cost. And in these 21 centimeter fast simulations, we want to do the opposite. We want to resolve huge cosmological volumes. For instance, we want to resolve the sun horizon of the baryons, which is 150 megaparsec. And these are the scales that are roughly measured by Hera, SKA, and so on. So our box is 1.5 gigaparsec in size. So you can see the successive zoom-ins here and here. And again, we lose the details of individual galaxies, accretion rates, merger trees, but we win this large parameter space and large cosmological volumes. So in brief, I'll show you a little bit about what this means for reionization. This model, we call it all galaxies because it includes the bright, the faint, and the molecular cooling. And again, the optical depth agrees with Planck because we made it agree with Planck. And then it agrees with different data points at low redshift. Compared to the older models, what you'll find is that we have more of a high redshift tail, again, because of the POP3 stars in molecular cooling galaxies. But it's unobservable by CMB, unfortunately, as far as we can tell. The biggest difference you'll find is in the global signal. So this is the 21 centimeter global signal versus redshift. Our all galaxies model is this black line compared to the bright and faint galaxies. And as you see, the timing is about redshift 15 or so. For reference, edges, peaks at redshift 17. But the depth is very different between the red and blue and the black. And that is because the new all galaxies model has the actual galaxy model within it matches the UV luminosity functions. So it has a star to halo mass ratio that follows the curve I showed you at the beginning. So it actually makes the different stages occur faster. So X-ray heating and Woodhouse field coupling overlap each other. So the black line never gets all the way down since X-ray heating happens before. And that was not the case in the red and blue. And this has been pointed out by Jordan and Jehong and others before, that when you actually match the luminosity functions, your global signal is flatter. This gives rise to much smaller 21 centimeter power because it's roughly the square of this. So you can see the black line here is about a factor of 10 smaller than before. It's still observable by things like Hera. So here in green is the noise you expect from 1 year of Hera. So you expect to still see this all galaxies model, but at a lower signal to noise than before. And if you go and see this in the power spectrum, you can ask what questions this can tell you about astrophysics and cosmology. First, about galaxies and astrophysics. I just want to plug this paper that Charlotte Mason, myself, and others are working on how to do fast inference from mock data. This in particular using Hera, where the idea is that instead of running expensive MCMCs, which require hundreds of thousands or at least tens of thousands of simulations, you can do a Fisher matrix that is very efficient. And it agrees surprisingly well with the full MCMC. So here the ellipses, don't worry too much about what the parameters are, just like the gray is an MCMC, the orange is a Fisher matrix and requires order 10 simulations, not that many. And finally, if you want to learn cosmology, you can actually do so as well. So I'm going to run the same animation as before, but now I want you to look at the top right panel, the power spectrum. You see as the signal evolves, this curve moves up and down, it's relatively flat, changes a little bit the tilt, up until about here, the X-ray heating epoch. You start seeing wiggles. And if you're familiar with low redshift galaxies, this will remind you of the baryon acoustic oscillations. But except these are not produced by some over and under densities, they're not at the percent level. These are some order unity wiggles. You can see it's a log plot. If I zoom in into this, this regime over here, you can see here the power spectrum versus wave number, and you see order unity wiggles in the 21 centimeter signal. And this is produced by these relative velocities, these streaming velocities that modulate the amount of galaxies formed in the universe. So instead of being sourced by densities like BAOs, they're velocity-induced acoustic oscillations given by these velocities. And they have the same sun horizon in them, which is why we need these large simulations to be able to resolve this. And by measuring these wiggles, we can, first of all, tell that there was velocity feedback. And second of all, gives us a standard ruler because we know RS. So we can go and measure the expansion rate of the universe, in this case, at redshift 15. And I want to point out that in this paper that we just finished, for the first time, we included all nodes and effects, including the actual light cone in the evolution of the signal, and the wiggles are still there. So I just summarize with conclusions that this has been a really fun conference to go to. So thank you to the organizers for putting it together. And my main takeaway is that the smallest galaxies will be hopefully measured by 21 centimeter. And we've been trying to model them in very flexible and computationally efficient ways to be able to learn maximally about them. Thanks.
Thank you, Julian. No, that was a nice recap of some of the things that we actually saw here. There are no questions at the moment on Slack. Okay, but we do have time for a few questions, so I can ask one, I guess. Oh, sorry. Okay, we actually have a few questions on Slack now. Okay. By Jordan, great talk. What do you assume about the X-ray luminosity per star formation rate and X-ray SCD for population 3 sources?
We assume it's the same as POP2. So we assume the X-ray luminosity per SFR is like 40.5, and it's the same SCD cutoff at 0.5 keV. We actually have another model that we run that is also public on the website, where we cut the SCD at 0.2 instead of 0.5 keV, just to see how much this changes results. And it does change a fair amount. But we assume that POP3 and POP2 do the same in both cases.
Oh, thanks. We have another question from Harley Katz. It's asking, when you model reionization, quenching of dwarf galaxies, do you take into account the inhomogeneity of reionization?
Yes, we do. So when I showed this curve here, this is the average across the simulation. But of course, the regions that reionize first quench the galaxies earlier. So every gas parts of the simulation has a different curve. This is just the average. It's a good question.
Okay. I think that's a wrap up for now. I'm guessing Aaron has some stats to show you.
So if you allow me, I would just like to take a few more minutes here. First, to thank all the high quality presentations of the many exciting ongoing work. I'm super happy. You know, this is the end of the conference, but I really hope that this becomes the beginning of people reaching out, talking to each other. Now you know what everyone else is working on. Start talking. There's a Slack channel for that, and everyone's email address is somewhere in the internet, so do it. Also, thank you to everyone who tuned in and asked questions. Without you, we can't have a conference, just people talking. We also have to have an audience and also good questions. So great. So let me do the organizer stuff for a little bit, since I don't get to organize conferences very often. Here is based on the responses from the Google Sheet, Google form. I know I turned off responses after the deadline for the abstract. So we advertise a lot and people do pop in, but this is based on whoever replied to the survey. So we do have a lot of people joining us from the US East Coast and also the UK and also Central Europe. But you know, for those people who are from the California area or the US West Coast, super early for them, or Asia, which is super late for them, kudos if you are here with us. So thank you for joining us from those time zones. And this is a distribution of people who sign up and their career stage. So we do have a great representation from grad students and postdocs, but we also have a good amount of faculty and staff scientist people joining us here. So great. I'm super happy. And also probably a lot of faculty people didn't sign up. So yeah, they're here. Great. So need more SIPs. There's actually one happening next month. So Masami Uchi and colleagues are organizing another one on early galaxy formation near and far and getting ready for long journey with JWST. So it's going to be exactly a month from now. So do tune in and see all those exciting talk as well. So let me see if I have anything else. And thank you all. I will upload this to the Slack channel in just a bit. And I'll turn to my SOC. Did I miss anything? If not, this is it. All right. Everyone take care. And the talks will all be, you can review them on YouTube shortly. All right. Goodbye, everyone.